Okay. So first off, thank you everyone for coming and attending this talk. Really appreciate it. So the Never-Ending Learner is actually a project started at Carnegie Mellon University by some of the top machine learning researchers out there. It's essentially a system that goes to the web, reads through the pages, and understands semantic material out of it. So just like how you and me would pick up a book, read, and try to gain new knowledge. And one of the cool parts about NELL, or the Never-Ending Learner, is it does all of this with very little human supervision, thanks to the advancements in semi-supervised learning. And actually it even posts its learning on Twitter, so you can follow it. So a couple of days back, it learned that broiled chicken is a type of meat, just like how I learned that biscuits and gravy is a breakfast here in the South. But the cool part is you can go back and you can see the provenance of that belief. You can see how it came to know that broiled chicken is a type of meat. And a couple of days back, and sometime back, NELL did something really interesting. It equated Donald Trump to a pile of wigs. And people were like, wait, that's kind of crazy. That's something that's totally unrelated. How did that even happen? And the researchers went back and they dug through the belief knowledge base that NELL had formed, and they discovered that NELL had crept into the darker places of internet, or as I'd like to call it, Urban Dictionary. So for all of you don't know what Urban Dictionary is, it is pretty much like what you would get if 4chan and probably Reddit trolls got together and recompile. But so it stumbled upon that, and over there, Donald Trump was defined as like a guy who can get hairstyles, a guy who's got cheap wigs on. So that's what it learned. And this is something that a semantic learner like not only NELL has been plagued upon, even IBM's Watson fell prey to this kind of weirdness. Eric Brown, who kind of is leading the project, gave an interview and he said when Watson stumbled upon Urban Dictionary, it started cussing like a drunk sailor. When one of the researchers asked a legitimate question to Watson, it replied with the F-bomb. So what does all of this have to do with my talk? At the core of this anecdote lies the fact that it does not matter if you have top leading researchers. It does not matter if you have a machine that just beat humans at Jeopardy. If you can control what goes into the machine, the algorithm, you can pretty much subvert it with very little ease. And that's what you're going to be hearing throughout this topic. And if there's one thing that you want to take away, that's what you should be. So, a little bit of like lay of the land here. This talk is a primer on adversarial machine learning, and I've tried to keep it as intuitive as possible with very little math. I will be showing you how to attack a small subset of algorithms, and I've chosen the algorithms such that they are quite popularly used. And I also follow them up with how you can, what are the strategies that you can use to kind of like defend yourself against these kind of attacks. I'm not going to be covering all the algorithms out there, given the restricted amount of time. But the end goal is for you to gain an intuitive understanding of how machine learning algorithms kind of work and how to attack them, and what you as a blue team member can kind of do to defend yourself against these kind of attacks. So, why do we care about machine learning? This is DEF CON. We should be talking about like remote code execution. Why machine learning? So first off, machine learning is used everywhere. I just plotted how machine learning is trending using Google Trends as a topic of study from 2012 to 2014. You can see there's a visible linear increase in machine learning. But the one quote that kind of stuck to me is what John Langford, he's one of the machine learning mavens at Microsoft Research. He said that machine learning is moving from an academic arcane discipline to an industrial tool. A lot of folks are kind of realizing that given the vast amounts of data that we can kind of get, and the huge increase in computing platform, we can pretty much make good, solid decisions using machine learning. And mostly, machine learning is now used in security more than ever. if you'd gone to RSA this year, you'd have and spoken to any of the vendors. They were all about like, oh, our system uses intelligence to catch APT. Everybody gave that pitch. And almost like weekly, I get a slew of articles and press releases in my RSS feed about every other company making a similar claim. So you see this whole deluge of wave on how to use machine learning even in security. And one of the things, again, that stuck for me is how DARPA is now investing tons of money into its next cyber grant challenge on how to use machine learning to catch attackers and to defend it automatically. The last time DARPA did this was autonomous driving cars, and lo and behold, everything is history. So there is a vast amount of interest in using machine learning in security. And before we go further, I want to just talk about what exactly is machine learning. And there's again, various interpretations to it. And I'm going to use the one that Pedro Domingos, a professor in University of Washington, gave in one of his lectures. If you look at the whole traditional programming paradigm, what you see is you give the computer system some data, and you give it a program that acts upon the data to get the desired output. So say that the data could be, say if you want to sort numbers, the data would be like an array of, say, unsorted numbers. The program would be, say, something like quicksort, whatever you choose, and the output would be this nicely sorted set of numbers. But in the machine learning paradigm, you're kind of only doing two switches. You're kind of bringing the output of the machine learning system is actually a program, and you're actually giving the output as an input to the system. So for instance, say in a network intrusion detection system that uses machine learning, the data would be, say, TCP packets or a full capture, and the output would be basically, you want to tell the system, hey, these are the kind of TCP packets that I think are anomalous, and these are the kind of TCP packets that I think are benign. And you would get, machine learning is not magic. It would give you a program that kind of helps you say from the data which one is benign and which one is malicious. So it learns from the data. So what am I getting at? For the model to be functional, for the program to make sense, the input data should make sense. And to get a bit more concrete, what am I talking in terms of a program? Is it just lines of code? It is, well, it's something more than that. What I get out of the program, or quote unquote program in the previous thing, is literally a bunch of numbers and weights. So I'm just gonna walk you through a quick example. If you've seen the graph, I just got the list of logons that happened in a particular that a particular account did in a system, and just plotted them. Just use simple Excel for linear regression, and what you get at the end of the output is basically a relationship between number of logons and time. And the numbers that I kind of highlighted, the 225 and the 875, is what gets stored as a model. It is what defines the whole linear regression system. And so it's not any fancy equation, it's literally a bunch of weights or numbers, or to generalize it, parameters that get stored. So even if you probably do, say, non-linear regression, you would still store a bunch of numbers, but the relationship would be different. So again, the takeaway is the data and parameters define the model. And if you as an end user can kind of control the data or get access to the parameters, you can pretty much change the model. So again, where do you find, before we go deeper into the talk, where would you find this kind of data? Where can you go and access these parameters? The data could be from many, depending on the architecture, could be from many points. For instance, it could be, say, if you're in a traditional SIEM architecture, you would have like the host machine that generates the data, or it could be the data could then be taken to a central storage and collected in a big data store, or even now with the rise of machine learning as a service, it could be in the cloud. And the parameters are generally stored in the code repository. So just like how you check in, do source control, it's pretty much the same thing with the parameters. And the second half of the talk, I'm going to say how do you kind of control these data and parameters for your advantage. So why do you still care? Now that you kind of understand, or I've told you that you can control the data and you can control the parameters, what can you do with it? And in order to kind of answer that question, I'm going to walk you through the anatomy of a general detection, machine learning detection system. So like I said in the previous slide, data is first collected. It would then, in a very generic setting, it would pass on through an anomaly detection system, and it's very imperative that the anomaly detection system actually sees the data that you're collecting. After that, if there's any anomalies and if there's anything significant, so the machine learning algorithm would pick it up, and finally the anomaly gets surfaced to a user. So this is like a very generic setting. Now if you as an attacker can kind of taint or collect the data or influence data collection or influence the data, you can pretty much have a cascading effect on the whole detection pipeline. Now, what does this mean? What do you get? What are the intangible goals out of this? First off, you can evade yourself from it. You know, the detection system would not be able to catch, would not be even able to detect your presence. Second off, you know, you could create a ton of false alerts. You could increase the false positive rates to crazy amount that the system becomes no longer usable. Or here's another thing that you can do. You can lead your incident responders astray. You can make them go through goose chases while you're kind of carefully architecting the system. And all of a sudden, the intrusion detection system has become like from your enemy to your ally. And just a quick note, as grown adults, there's a huge obsession with unicorns. This is the third time, I think, in the whole from the keynote that we have a unicorn in a presentation. So it's something for us to go and think about. So putting it all together, why do you care? Why do you want to attack machine learning? First off, there's huge opportunity there. Machine learning is being used everywhere. It's pretty prevalent in the security system with the rise of anomaly detection. It's pretty easy, as you will learn from the talk, that if you can control the data and if you can control the parameters, you can pretty much subvert the system, and and lastly, you have a very high rate of return. If you can subvert a machine learning system, you can pretty much treat it like your puppet. So, switching gears a bit. In the next part of the talk, I'm going to be walking through some practical attacks done on machine learning systems. And the framework that I'm going to be using is, I'm first going to give a very intuitive understanding of the algorithm. Then I would give you how the system looked before an attack, how the system looked after an attack, and what are some of the takeaways that you want to take from each of this algorithmic implementation. That's going to be the lay of the land for the next minutes. So, the first, just a bit of history here. So the data set that I'm going to be using is called the Enron spam data set. So when the Enron Corporation was being investigated by the federal authorities, they kind of released the emails that happened within the corporation to the public. Andrew McCallum, one of the researchers in University of Amherst, he kind of bought the email and he kind of gave it to all of the researchers out there. It's a publicly available data set, and it's one of the standard data sets that anybody would use to kind of like test their machine learning system if it's able to kind of work well on a real world setting or not. So roughly there are, after you clean up and remove the duplicate messages, you roughly have around like 200,000 messages. So that's the data set that I'm going to be using. So imagine that you knew nothing about like spam or ham, and all what you're going to be hearing is, and this is all the knowledge that I'm going to show you. So I literally picked out messages from the spam folder and the non-spam folder. And in the spam folder, you can see things like, the subject lines indicate like Valium, Cialis saved my family, order Viagra, things like that. And the ham emails are pretty much like reports and assignments and things like that. What you generally see in a folder. So if you had no knowledge about machine learning, if you had no knowledge about spam and ham, What do you think the first message is? Do you think it's a spam or do you think it's a ham? It's just, for those of you at the back, the subject line reads assignments, assets, group. So just base your knowledge on the previous slide. The second subject says, Valium, Viagra at lowest price. So let's just take a call. First message, how many of you think it's spam or ham? Spam. Do you think it's, I think it's ham, do you agree? The second message, do you think it's spam? Okay, so again, no machine learning, just based on the previous slide that I showed you. What your brain actually does is it constructs a joint probability distribution table. So, or in other words, it looks like, okay, so assets occur more times in ham messages than spam messages. And say Viagra or Valium seems to be occurring more in like spam messages rather than benign messages. So if I were to just take a subject and say that, assets, assignment assets group, the way, and this is the algorithm that I want to explain naive Bayes does is it takes what's called a bag of words model. So you just take all the words, you put it in a bag, you shake it up and throw, and or in other words, you do not even think about context anymore. You just go up, you see assignment, you see what probability it has, assets, what probability it has, and whichever, and group, what probability that word has, and you calculate, given this message, is it a spam, or given this message, it's a ham, which one is more probable. So if I were to do this spam given ham, none of the words occur, so it's kind of the probability of that being spam is almost 0. And if I were to just think if it's a ham, I get like a non-zero number, and since 0.14 is greater than 0, the message is more likely to be ham than spam. So that's kind of like a very simple example. But naive Bayes algorithm is really powerful. If somebody were to give me a large data set and say, okay, try to get some conclusions. This is kind of like my go-to algorithm to begin with. And that's exactly what I did. I just built a very naive, vanilla naive Bayes classifier. I did have to do some sort of normalizations because I had to remove like stop words like is and was and things like that. And I ran it on 80% of the data set. And my goal is, hey, given a new subject, can I predict if it's spam or ham? And I tested on 20% of the data, and it gives me a good test accuracy. So 62% of the time, it's doing much better than random. It's able to kind of accurately say whether if it's a spam message or a ham message. Now, the attack that you can do with naive Bayes is pretty simple. It's actually called, very funnily, it's called a good word attack. So what you basically do is you introduce innocuous words into the message. So, you put in you disguise your spam messages, by putting more innocuous words, and the test accuracy dropped to a significant 52%. So now the system is just taking a blind guess. It's as good as asking a toddler, hey, what do you think this message is? So there's no machine learning at all that's happening right now. And here's the best part about this naive Bayes algorithm's attack is that the more innocuous words that I actually kind of started introducing, the false positive rate started skyrocketing. So if I took a spam message and I added 10 words, the false positive was pretty normal. Say 20%, I can kind of accept it. But by the time I hit like 10 to 20 words, it was getting wrong most of the time. So what's the takeaway here? If I just implemented, if somebody were to implement, an email classification system with just naive Bayes, you can pretty much start disguising your spear phishing emails by just padding with innocuous words. Don't worry, people have gotten more intelligent with that. But the bigger takeaway is just by manipulating the data, the input to the algorithm, I can pretty much I have increased the false positive rate, and I can make the system unusable super quick. So that's like the biggest takeaway of this kind of first exercise. The second exercise algorithm that I'm just going to walk you through, and I'm going to be switching context, is support vector machines. Support vector machines is actually Ferrari of machine learning because it's immensely popular. It has a really cool sex appeal to it because it's quite fast, and it actually delivers a pretty solid performance. Many people call it the black box, which is kind of questionable, but that said, it's used widely in a classification setting. I actually pulled some market material from a very well-known malware analysis company that has said that, oh, it's now math versus malware, and they now use support vector machines for it. There's also been a lot of interesting research and a lot of interesting systems that have now started using, because of how fast it is, to analyze malware. So given a piece of code, is it malicious or is it benign? Or if you're in a or what kind of malware it is? You can also ask those kind of interesting questions. So in order to first give you like a quick intuition about support vector machines and how they kind of go about, just imagine that you have a set of positive examples. And imagine that you have a set of negative examples. Let's just assume they're pretty nice, linearly separatable. The support vector machine literally tries to learn in a two-dimensional setting a line that divides the positive examples from the negative example. It's literally but in other dimensions they call it hyperplane. But that's what support vector machines are trying to learn. So this could be one line, but that kind of like divides both these examples. But another reasonable person might say, hey, what about say this line, or what about this line, or what about this line? So all these lines all these lines are, to formally call them, these decision boundaries are equally possible. So the question now becomes, which is the right one? Which is the most optimal one? That's what support vector machines are literally trying to solve. And the intuition behind support vector machines is it will pick the line, or it will pick the decision boundary that kind of separates that has the maximum margin from the support vectors, or to be more accurate, so it would look at the points along the boundary, and it will try to distance itself such that it separates the boundary as much as it can, or the margin between the boundary points are pretty high. That's the kind of intuition behind support vectors. And the most important part about this are these boundary points. And that's what is called support vectors, which gives the algorithm its name, support vector machine. So these points on the boundary are super important, and that's what defines the end output of a support vector machine. So the output, in other words, the output of SVMs are these support vectors. And and the reason why they're so fast is you can pretty much, after you train on the data and you get the support vectors, you can pretty much discard the rest of the training set. And all you need to be storing is that particular support vectors. So think about it. If you have, like, say, gigabytes and terabytes of data, once you've trained on them, you can pretty much throw away, and the support vectors can literally be stored in memory under your desktop. That's why they're pretty important. And the takeaway here is a good part of the model is determined by the support vectors. And if you can control the support vectors, you can pretty much control the whole model. And that's pretty much what I did. So in this figures, I've kind of like highlighted the support vectors with these circles. So if you see in the original model, the support vector is pretty much done, like figured out decision boundary with reasonable effort. And all that I did over here was I flipped one of the labels of the support vector. So so the green represents, by the way, positive, and the red represents negative. And all that I did was I flipped one of the labels, and the decision boundary drastically changed. So just by changing this data point from a positive example to a negative example, I pretty much could control how the SVM system is pretty much working. Again, in a real world example, it could, especially if you're you can pretty much craft examples of a malicious piece of code and make it benign. And you can pretty much, and if the system were to use, say, support vector machine, you can pretty much control its decision boundary, which means you can pretty much control how it classifies if a given piece of code is malicious or if it's benign. So that's, and all of this is just by flipping one label. And going to the third algorithm in clustering, it's one of the widely used learning algorithm for anomaly detection. So if you, I mean, there's like a lot of, once again, a lot of market speak out there, a lot of companies out there kind of publicize the fact that they use clustering, and it's for good use. So imagine that you have this setting wherein, like, again, the red points are malicious data, and the blue is benign data. Clustering, I just ran a simple k-means algorithm. The clustering kind of, just like how in support vector machines, the parameters are the support vectors. In the clustering algorithm, the parameter, or the one that decides, are these 2 points. It's called the centroids. So just like how in support vectors, once the centroids is kind of determined, you can throw the rest of the training data, and by practice, the only ones you store are the centroids. So how is it used? So given a test point, just like this yellow point that comes in, is it like, say, malicious or if it's benign? All that you need to be doing is you compare the distance between the centroids, and whichever point it is closer to, it would the system would kind of automatically assign that label to that cluster. So the attack intuition over here is pretty simple, but actually you'll come to know in practice it's more difficult. But say that you've built a system that kind of has baselined what is considered to be normal traffic through your environment. Say there's an attack point that say an attacker wants to kind of increase the false negative rate, and he wants to go pretty much go disguised. So he wants this attack point to be included. The way you want to be doing is you want to be able to shift the center or the centroid in the direction of the attack point. And that's pretty much what, again, I did with this simulation right here. As you can see, all that I kept doing was I kept adding more benign, intelligently crafted benign messages, and slowly you see the points in the border of the malicious traffic are now slowly starting to get converted as benign traffic. Again, the takeaway that you want to get from this slide is that in order to attack the algorithm, I'm not even in the case of support vectors, I'm not even manipulating the parameters. I'm just sending data as part of normal traffic. And that is why subverting machine learning algorithms are so powerful, because the system really cannot distinguish whether if it's normal or if it's benign normal. And just by doing this, I've kind of increased the false negative rate, which means the system would not be able to classify known benign traffic as known malicious traffic as malicious. So, in summary, by showing you a sample of these algorithms, you can pretty much make a system start giving so many false positive that becomes unusable. You can evade detection by increasing the false negative, or you can pretty much make it do whatever you want by having control of its decision boundaries. Those are kind of like, the different attacks and what you could do with those kind of algorithms. Now, when I'm going to be talking about defense, the run through that I'm going to be using is what are some of the techniques, to kind of, you can use before deploying the system. What are some of the table stakes? What are the things that you must absolutely do as not best practices, but you should be doing when you're designing a machine learning system? And what are some of the machine learning techniques that you can use to make sure that it doesn't get attacked? So, when you're kind of, the first step, of course, is threat modeling. And this is something that, as developers in your organizations, that would do is as you're defining the adversary's goal, you want to ask yourself, hey, is my adversary's goal, is it, say, to evade detection? Is it to screw up my recommender system that, say, Netflix had built? Is it to screw up, say, the ranking algorithm of the search engine of this company? So you first want to be able to define in adversarial what the adversarial goals are. And the second part is you want to ask yourself, what does the adversary know about my system? So does he know my training set? Does he know, for instance, what are the features that are in the system? What kind of learning algorithm I'm using? Now, one of the questions that people generally ask is, hey, do I have to keep the learning algorithm a secret? If the attacker does not know what learning algorithm I'm using, I'm pretty much safe, right? Well, that's not necessarily a good intuition to have, because everyone knows, for instance, Google uses PageRank to kind of sort the results. It's public knowledge, just like how everyone would know the algorithm for AES encryption. So the algorithm itself need not, I mean, if you can keep it a secret, and security by obscurity is never a good strategy to follow anyway, it's okay. But even if the attacker knows the algorithm, the one thing you really want to wrap up is the features. And I'll talk a little bit more about that in the next slide. And so you want to ask yourself, what kind of knowledge does my attacker have? Does he have partial knowledge? Does he have limited knowledge? And depending on that, that would kind of really affect how you're designing your machine learning system. And what is the attacker's capability? For instance, especially in the machine learning system, in adversarial machine learning system, you want to be able to ask yourself, hey, does the attacker have the ability to modify only a small subset of my training set, or like everything? Say in the email example, an attacker will have direct influence on the email messages. He would be able to send email messages, but he might not have control over the metadata. Just like how in network packets, he might be able to modify the contents of the packet, but it's pretty much more difficult to work with the metadata. So you might want to be able to think about what are the capabilities of the attacker, especially in an adversarial machine learning setting. So what are the table stakes? The first thing that you want to take away, the second big picture that you want to take away from this talk is that you want to be able to secure your log sources and secure your storage space. So you want to be able to have a lot of so given, or to put it differently, given a log source or given a log data, you want to at least make it either tamper evident, if not tamper proof. So it makes it really difficult for the attacker to spoof messages. And on a very related note, you really want to be monitoring your data quality. That is something of very low effort that can give you very high returns. Say, for instance, in the previous example, if I just monitored the volume of benign traffic that was flowing, and say there would have been a huge spike in the benign traffic, and I would know something is wrong. So that is another absolute minimum that you should be following, especially in an adversarial machine learning setting. You also want to be able to make sure that you're treating these parameters, say in the case of SVMs, those were support vectors. In the case of the pre-clustering, there's the centroids. You want to be able to treat them as secrets. And another thing that people generally are doing, which you never should be doing, is use publicly available data sets to train your intrusion detection system. So don't use, especially in an AV classifier setting, you don't want to be using only publicly available knowledge, because the same data sets are pretty much available even to an adversary. So he could pretty much test it on that system before he tests it in yours. And when designing your system, try to avoid as minimal amount of interactive feedback as possible. So those are kind of some of the table stakes that you want to be thinking about. And moving to the last part, what are some of the machine learning techniques that you can kind of use to combat this problem? And the first one is ensembling, and this is, I included that with a lot of bias because it's my favorite technique. Because, and to give you a high-level overview of ensembling, and this is so intuitive, is that think about Who Wants to Be a Millionaire game. I'm sure most of you would have seen it. So if the contestant doesn't know the answer, he would ask the audience, and he would go. So you're trying to use the wisdom of the crowd almost to get the right answer. And it's the same principle that you can follow in ensembling. So basically, you use separate models to kind of independently assess if a given session is, say, malicious or benign. And the beauty of the more intelligent part of this is you want to be able to choose models where you're supplementing them well. So where one model, like say naive Bayes, is failing, you want to probably use a different algorithm to pair it up with. And so each model would independently assess for maliciousness, and there are many techniques that you can use to combine the output of these individual detections. So I did the same thing. I just in my spam or ham example, instead of just using naive Bayes, I used linear SVM, and I used Gaussian naive Bayes. It's another algorithm to kind of supplement the system, and I just use a simple majority, just like how you would. So if I use 3 algorithms, if 2/3 of them kind of say it's malicious, if it's spam, I would call it a spam. So, and here are the results. The green one indicates, with ensembling, and the red one without ensembling. So for the same amount of benign words that I added, while ensembling is very intelligently, at least it's only 40%, you see that without ensembling, just if I had only used naive Bayes algorithm, I'd have gotten a very abysmal false positive rate. So again, it's a very simple thing that you can do to kind of like buttress yourself from these kind of attacks, especially data manipulation attacks. The second thing that you can do, and this technique is as old as the hills, is use robust learning methods. So it's robust because the system kind of would treat outliers as noise. So just when I flip the label, you can see that the robust SVM pretty much gives the similar boundary as the original one. So the effect of the boundary is pretty much kept constant. But I do want to mention like a couple of things here. So here's a list of algorithms because of want of time, just like how you have this eat this, not that. I pretty much compiled what are some of the better alternatives to like the existing algorithms, and I've also hyperlinked them to the source. They're not any malicious links, by the way. And a word of caution here. One thing that happens is, the pros are, yes, it's a well-studied field. There are a lot of choices with robust learning mechanisms. So, people have looked at it from all perspectives. Like, for instance, how can I optimize if an attacker is in the internet? Or that's a very optimization way of looking. Or in a game theory way, people have defined algorithms like, okay, so the attacker knows this much about my system. I know so much about the attacker. Is there like a nice Nash equilibrium that I can kind of attain on? So yeah, there are many choices. But the cons is, the first thing is the performance would take a hit, because these kind of robust algorithms, for the most part, I'm not saying all of them, they're more complex than standard algorithms. So if I'd only used like a standard SVM, it just took 10 minutes, I could run it out of my box, single node implementation. Again, I'm not using any kernels, it just took 10 minutes. But, when I did a robust SVM, like one I showed before, it took almost like 6 times the amount of time it took to run that. So be careful so if your system involves some sort of like real-time guarantees, you want to be cautious of that. And the second thing is, all these kind of robust learning techniques require a lot of tuning and a lot more babysitting. There are so many more knobs and parameters to kind of turn in these robust techniques. It becomes a pain, especially if you're kind of like going to retrain the model in a couple of months' time. So that kind of is the end of like how you can use machine learning. And here are the 3 things that you want to be able to take away from this talk. If all the others kind of like didn't fly through you. The first one is machine learning algorithms are pretty much susceptible to attacks. You really you can evade the system, you can make the system unusable, and you can even take entire control of the system. The second thing is there are in the most part, you can do little techniques like monitoring the data quality, securing the log storage, and securing the log sources is some of the easier ways that you can get away from these kind of attacks. There are complicated methods, but again, just because of an open bias, ensembling is one of the easier ways that you can get good benefits out of it. So that pretty much brings me to the end of this talk. So if you have any questions, and do we have time for questions? Okay. Happy? Yes. Awesome. Okay. Thank you very much. Appreciate it.